Okay, let's continue example 2. A system composed of n separate components is said to be a parallel system if it functions when at least one of the component functions, right? We can check from these parallel systems, and it's like a circuit, right? Circuit. For such a system, if component I, which is independent of the other component, functions with probability pi. So each component I, the probability when it works is pi. When it fails, then it's 1 minus pi. What is the probability that the system functions? So from here, you will understand that, yes, it's the same as the case A in the previous example, which means at least one component works, then the whole system will functions, right? The functions means it works, right? That is like the parallel system in the circuit. The current flows from A to B. If one of them works, then it's connected from A to B, right? So but here, each component works, the probabilities pi depends on I. They are not always p, right? They are not always p. So let event A, we can write in this way, okay? Let event A be at least one component, right? At least one component works, right? At least one component works. So that will be, how can we find the probability of A? You can do 1 minus the probability A's complement, right? What does A's complement mean? The event A's complement, which means all the n component does not work, right? All the n component not work. The probability is 1 minus pi, right? 1 minus pi. So the probability not work for the first one is 1 minus P1, right? The first component not work, the probability is 1 minus P1. And then the second component, the probability not work is 1 minus P2. So it's 1 minus Pn. They are not the same P, right? They are not the same P. For the product, you can write it in this way. So product, you write in this symbol, okay? It's not Riemann sum, but similar to that. The index I from 1 to n, 1 minus pi, right? That means the m product of 1 minus pi. We can write it in this way. So it's pretty easy, okay? It's pretty easy. And each component, here we make use of the independence, okay? The independence. So here, the first one work. The first one work, the probability is P1. The second one work, the probability is P2. The third one is P3. And until the last one is Pn, right? If they doesn't work, the probability will be 1 minus P1. All of them will not work. All of those n components will not work, so will be 1 minus P1 times 1 minus P2. Take the product of those n failures for the n component, right? So trying to understand the first one, okay, the first example and the second one. The first one is the a sequence, okay, a sequence of independent n trials. We will see this kind of examples a lot in future. And the parallel system, okay, the parallel system, how to make the flow from A to B connected if the circuit becomes more complicated, okay? Here it's pretty easy. Only at least one of them is works, then the flows from A to B is connected, right? And there might be more complicated circuit. you will saw in the circuit. I guess you will take your circuit class in future. Okay, that is also important part for engineering students. So that is example 2, pretty easy to work out the answers. Now let's check one more examples. It's also play around with the uh, at least, okay, those stuff. Example 3. Suppose there are n types of coupons, and at each new coupon collected is independent of previous selections, which means out of the n coupons, each one is selected is independent, okay, is independently. A type I coupon with probability pi. So you have the probability pi to choose the type I coupon, depends on the i's, okay. Of course, the probability you choose all the n coupons, that will be 1, right? That will be 1. Suppose n coupons are to be collected. If AI is the event that there is at least one type I coupon among those selected, then for I not equal to j, find all those 3 probabilities. Let's work out one by one, okay? Let's work out one by one. So the AI means at least one type I coupon among those selected, okay? At least one type I coupon, okay? Type I coupon. And it depends on I, right? At least type I coupon among those K, right? Among those K collected. Among those K collected. And we know the I can be one starting from 1, 2 until n, right? Just means you choose at least type 1 coupon among those K, right? Among those K. So the probability of the AI, you can think about the AI's complement, right? AI's complement, which means the I's coupon type I coupon is included in those case collected. What is the complement event? Which means type I coupon not collected, right? Type I coupon not collected. Type I coupon not collected for those K, right? Among those K. Type I coupon not collected among those K. Here we just collect the coupon. It's different from the trials, okay? It's different from the trials problem. So the probability of AI will be 1 minus the probability of AI's complement, right? Of the AI's complement. Then type I coupon, right? Type I coupon was not selected. So for each one, okay, for each one we have K. We are going to collect K, right? We are going to collect K. So the first one, second one, the ice one, and until K. This is the collected, right? Collected K coupons. Each coupon, each one, okay? So this one is not A, right? Is not I. Not I. Second one, not I. We are thinking about the probability for AI's complement. Then for the ice is also not ice type coupon. And for the case one is also not I. So what is the probability to choose the coupon, to choose the first one, to choose the first coupon which is not the type I? Of course, it's the probability 1 minus pi, right? So which means you choose the other n minus 1, right? But what is the probability you choose the other n minus 1 coupons? 1 minus pi. Or you can write the summation of the other n minus 1, right? The other n minus 1 probability is the same as 1 minus pi, right? So the second one is the same. The second, when you choose the second coupon, what is the probability not type I? It's the same. It's the same. It's the other n minus 1, right? With the probability 1 minus pi. So the nth, it's the same. The nth, if you are not going to choose the type I, you choose the other n minus 1, right? The type is different, right? We mark the type 1, 2, 3 until n, and those are the positions for the k collected coupons. And until the case 1, the case collected coupon, it's not I, so the will be the other n minus 1, right? The other n minus 1. To choose the other n minus 1, the probability will be 1 minus pi. So what is the probability type I coupon not collected among those k collected coupons? So that will be 1 minus pi to the k, right? So that is the probability for the eighth complement. And here it's a different because the probability to be selected for type I coupon is pi depends on the I, right? Depends on the I. So this pi depends on the I. They are different, okay? They are different. Might be like when the probability to choose the first type 1 is 0.1, type 2 is 0.2, type 3 is 0.25. They are different. The first example, the probability to get success in n trials, for each trial, it's the same, is the probability p. And the probability to get a failure, it's all the same, 1 minus p. This is a little different, okay? This is a little different. So that is part A, okay? Part A, it's pretty easy, okay? It's pretty easy. Just to try to understand what does even AI mean. Let's check the second one, okay? Let's check the second one. What does AI union AJ? J and I are different, right? I not equal to J. So AI means the event there is at least one coupon I among those. And J means there is either type I or type J coupon collected, right? Union means either type I coupon included in the K collected, or either type J coupon collected, or either both type I and type J coupon collected. That is what the union event means, right? So either type I or type J coupon type J coupon among those and those K collected, right? It should be one of them or both, right? You can think about the complement of this one using the De Morgan's law, okay? De Morgan's law. That will be AI's complement and AJ's complement, right? Apply the De Morgan's law. The complement of this event will be AI's complement, AI union AJ's complement. Then that will be each complement intersection. Now intersection, this is more straightforward to understand this one. So AI's complement means type I coupon is not included in the K collected coupon, and this means type J coupon is neither among those, right? So which means neither type J nor neither type I nor type J coupons among those K collected coupons. We only collect K coupons. Now, how can we understand this event? And we know that the probability of AI union AJ, you can work out in this way, will be 1 minus its complement, right? Its complement. AI union AJ, the whole thing complement, right? The whole thing complement. Let me write in this way. Try to take notes and understand the logic. Okay, understand the logic. So we need to work out the probability of this one. Okay, AI's complement, AJ's complement. Now AI's complement and AJ's complement means neither type I nor type J coupons among those K collected. Now we still have those K coupons, okay, to collect those K coupons. So first one, second one, the I's one, and then the K collected. Then for the first one, we are going to choose the other n-2 coupons out of the except the type I and type J, right? So what is the probability you choose the other n-2? So you can write P1 plus P2 plus Pi minus 1 plus Pi plus 1. So we should remove the probability for for type I and type J and then the others, right? So you can understand it this way: 1 minus Pi minus Pj. Make sense? Pj. So which means the probability we are going to choose the other n-2 types without choosing type I and type J coupons. How about the second one? The second one is the same, right? Let me write here. Let me move the probability here. So for the first one, not I and J, you are going to choose the other n-1, then the probability will be subtract Pi and Pj from 1, right? And then the second time when you collect the coupon, this is the times you are going to collect it. Those are not the type, okay? Those are the K coupons you are going to collect it. So the second time you are not going to choose I and J, right? So the probability you are going to choose the other n-2 will be 1 minus Pi, 1 minus Pj. And then until the last one, you're also going to choose the other P-2 coupon without I and J. So the probability is the same, right? The probability is the same. So what is the probability for I's complement and AJ's complement? So that will be 1 minus Pi minus Pj. We have K, okay? We have K. That will be much easier or more clear to think about the complement, okay? To think about the complement. You can also do in this way, okay? You can also do in this way, like either type 1 and type J coupons. So you can follow the probability, okay? You can follow the addition rule to work out this probability that equals Pi plus Aj minus probability AI intersect AJ, right? AI intersect AJ. We can follow in this way, okay? We can follow in this way. And let's check this probability. That will be more complicated, actually. That will be more complicated. So we know how to find the probability of AI, probability of AJ, right? These two parts is easy according to part A. But what does this one mean? What does this one mean? This means at least, this means the I's coupon collected and the J's coupon collected, right? The I's coupon collected and the J's coupon collected. And when you think about both two coupons are selected, are collected, and you need to think about their position, okay? You need to think about their position. So it will be more complicated to work out this one, actually, because you can put, for example, you can put your ice coupon on the first position and the second position. So to think about, let me explain this one, okay? Why we didn't work out in this way. And usually there is not a unique solution, okay? There is not a unique solution to work out the probability, but we are trying to figure out the more convenient or more clear way to work out the probability. So here the probability of AI and AJ, right? If we are going to think about this part. So the event, let's think about the event AIAJ. So that means type I coupon and type J coupon collected, right, are among those K collected. So let me write the sequence. You might have 1, 2, until the I, until the K, right? So this is the first coupon, second one, the I's one, and until the K's one you collected. Type I and J, type I and type J coupon are among those. You might have type I here. You might have the other, okay? Let me just write other, which means out of those two, okay? Out of those two. Neither type I and type J. The other n minus 2. So you might have at the ith position, you choose type J, and then you have the case one, the last one is the other. Or so you will have different combinations to put this I and J, okay? To put this I and J. You can also figure it out, but it becomes more complicated. I just let you know it becomes more complicated. So those are still the K collected. So you might have this is the others, and then you choose the second one is type I, and then the other, okay, the other. This is type J, right? So you have several combinations when you choose type I and type J, right? Type I and type J. So that becomes more complicated, right? That becomes more complicated. That's why we use the complement to think about the AI using AJ's complement to work out these examples. And let's think about part C, okay? Let's think about part C. You can also consider the example in that way, but maybe more complicated. So here, solve part C, this is the conditional probability, right? Conditional probability. So that means given type J is collected, what is the conditional probability type I is collected, right? So AI, let's understand this probability, okay? Let's understand this conditional probability. So this means the conditional probability for AI, conditional probability for type I coupon collected among those K, right? Collected among those K. Given the type type J coupon is collected among the K. They are different, okay? They are different. Those K collected. The event AI given AJ and this event AI and AJ and this event AI union AJ, they are all different, right? They are all different. Try to interpret those events, okay? Try to interpret those events. The first one means given, which means we know type J coupon is among those K collected, is already collected among the K coupons. The conditional probability, the type I is also included in the collected K coupons. That is conditional probability. The second one, AI and AJ, which means both type I and type J coupon are collected among those K. This one means either one of them, either type I or type J are included in the K collected. So trying to understand the different interpretation for those events, okay? Now, according to the definition of conditional probability, we can write this is the probability AI and AJ over the probability AJ, right? And according to part B, we have already figured out the answers for part B. And according to the addition rule, we know the union probability is AI plus probability of AJ minus the probability for the intersection, right? So from here, we can rewrite the intersection probability, which is probability of AI plus probability of AJ minus the probability union, right? Minus the probability union. That gives the intersection and over the probability of AJ, right? So according to part A, the probability of AI is 1 minus 1 minus pi to k. Now the index becomes j, so it's j, right? According to part A, the answer is 1 minus pi to the exponent k. Now we change the index into j, right? That is the probability for the event aj. That is the denominator. And according to the part A again, so this is 1 minus pi to the exponent k. This one, that is probability for event ai plus 1 minus p j to the exponent k, right? The first part, the second part, and then subtract the union. What is the answer for the union? The answer for the union will be 1 minus pi minus pj, okay, right? That is the union, right? We work out in the part B. So that is the final answer, okay? That is the final answer for part C. And this formula to write the conditional probability formula is easy, but we need to figure out each part, okay? We need to figure out each part. And for all those examples, we think about the independence, right? Independence of each trials of each component works of each coupons to be selected, right? So that is the examples we would like to discuss in the independence event in the section 4. Now let's start the section 4, okay, section 5, sorry. Section 5, the conditional probability given the event f, okay, we just follow the notation from the textbook. The conditional probability given the event f, this dot can be any other event, right? Any other event. This is also a probability, okay? If we have this conditional probability given the given event f, that is also the conditional probability is also a probability. What does this mean? If this is also a probability function, that satisfies the axioms of the probability we studied, right? Now let's check the axioms, right? Let's check the axioms. And here, of course, the E is any subset, right? E is any subset of the sample space. So let's check the proposition 5.1. The conditional probability is the probability. Of course, the probability should be between 0 and 1, right? And given part B, given the event f, the conditional probability of the sample space S equals 1. Part C, if EI a mutually exclusive event for the I starting from 1, 2 until infinity, then the probability of this union given the event f, that is the sum of each conditional probability. So this is similar, right? This is similar. We just work the conditional probability. We use the conditional probability to follow the axioms of probabilities, right? Now let's simply prove those, okay? Let's simply prove those. So probability, let's, according to the definition, okay? According to the definition, with the definition of conditional probability, with the definition, so probability of another event E giving F. Here we are talking about the conditional probability. Of course, they are not independent, right? They are not independent. So that will be probability E and F over probability of event f. And when we write this conditional probability, we know that we assume, right? Assumed the probability for the event f will be positive. It cannot be 0 as the denominator, right? So since those are probability, right? Those are probability. Since probability of f is positive, and this is also E and F is another event, right? E and F is another event. So this is the probability function that also satisfies between 0 and 1, right? Between 0 and 1. Sorry. So the top is between, the top can be 0, okay? The top can be 0. The top is the probability, is the number between 0 and 1. The bottom is the number positive. Of course, then it should be positive at least, right? This is positive or can equal to 0 when the top is 0. There is no problem, right? There is no problem. This is a non-negative number, the probability. Then how can we prove? How can we prove this part less than 1? Let me write in this way, and let me explain. The intersection E and F is the subset of F, right? This one. Intersection is the subset. There is no problem to understand this one, right? Intersection E and F is the subset of F. If you use Venn diagram, it's very direct, okay? It's very direct. And we have a result. If this, the left side, if this is a subset of F, then the probability of E and F will be less than or equal to the probability of even F, right? And since probability of F is positive, right? Is positive, then probability E and F over probability of F is less than or equal to 1. So we have this fraction, right? This fraction is between 0 and 1, okay? Between 0 and 1. And what does this fraction mean? This is the conditional probability of event E given F. So we proved, okay? We proved. So part 1 proved. Part A proved. And let me mark it, okay? Denote, proof is done. So that is part 1. Second part, the sample space, conditional probability of the sample space given the event F is 1. Event F is the subset, right? Event F is the subset. And let's rewrite the conditional probability according to the definition. That is sample space and F over the probability of F. What is the event? What is the event? The sample space and F. Sample space, just think about the Venn diagram. Sample space is a whole rectangle. Then the F, event F is the subset. Event F is the subset, right? F is the subset of the sample space. Of course, the intersection of those two will be the event F. Event F's probability over event F's probability. Of course, that is 1. And we know it's always, when we give in the event F, that is always positive, right? Always positive. So it's straightforward to prove part B, okay? Part C, okay? Part C. If the events are mutually exclusive, then the probability of conditional union, that will be the sum of each conditional probability, okay? That will be each conditional probability. Now, still, let's follow the conditional probability, okay? And this union, we are going to apply the axiom of number 3, right? We have already know if they are mutually exclusive according to axiom number 3. We know that follow axiom number 3. How can we reach the result, or how can we apply the axiom number 3? So let's recall the axiom number 3, which means the probability of union all those EI, and we know this EI infinite sequence, they are mutually exclusive. That will be the sum of each event probability, right? If the sequence are mutually exclusive, right? We know this result from answer number 3. Now let's rewrite the conditional probability. I starting from 1 to infinity ei. This union event given event f. According to the definition, that will be the union ei and this union and f, right? And f, and then over the probability of f, right? So how can we expand it this one? How can we expand it this one? The union of ei and f with the distribution law, that will be the union for ei and f. Each ei and f, then take the union, right? Each ei and f take the union with the distribution law and over the probability of f. Now since ei for I from 1, 2 until infinity are mutually exclusive, how about ei and f? Those are mutually exclusive. So how about ei and f? Ei and f is the subset of ei, right? Since ei are mutually exclusive, of course the subset. So ei and f, they are also mutually exclusive because they are subset for each event ei, right? So which means mutually exclusive means ei and ej are null event for I not equal to j, right? Of course, ei and f intersect ej and f because this is the subset of ei. This is a subset of ej. Of course, the intersection of those two are null event for I not equal to j, right? So eif for I starting from 1, 2 until infinity, they are mutually exclusive. Why we need the mutually exclusive? Now let me just continue on another page. We stop here, right? So we rewrite the conditional probability infinite union ei given f as this one over the probability of f. Now with the distribution law, that will be the union, right? That will be the union ei and f, right? Ei and f, I starting from 1 to infinity. And we know ei f are mutually exclusive, right? And you can take this one as ai as a new event, actually are mutually exclusive for I starting from 1, 2 until infinity, right? Those events. You can take this as a new event ai. So the event ai is mutually exclusive, and when we take the union of those, apply axiom number 3, right? Apply the axiom number 3, we can get the top is the sum of each probability ei and f over f, right? Over f. And since it's divided by the probability of f for each term, so we can rewrite in this way. Take the Riemann sum outside, that will be each probability EI and F over probability of F. What does this fraction mean? This fraction actually is when you write EI, even EI giving F, what is this one? That is probability EI and F over F, right? Over probability of F. So the fraction actually means the probability EI given the event F, the Riemann sum. So that is what we proved, right? Part C proved. Right? That is the Riemann sum of the each conditional probability. Right? Riemann sum of each conditional probability. So for section 5, okay, for section 5, the conditional probability is also a probability. So that means they all satisfy those axioms. We write it as a proposition 5.1. And there are more examples in this section, and which I think are more advanced, okay? More advanced. So we are going to skip all the examples in this section. So in this section, we are only limited to this proposition. Okay, if you check another reference book, so for the conditional probability part, if you understand this is the probability, satisfy those axioms of probability, that will be enough. Okay, we are not going to give any examples. That will be more complicated case. We will skip that. So that means we are done with the chapter 3. Okay, chapter 3. So let's go through a little quick to review the summaries. Okay, to review the summaries. And it's almost time. We are not going to start chapter 4. We will start chapter 4 next time. But let's go through a little quick for the summary of chapter 3, the conditional probability and independence. Okay. So for event E and F, the conditional probability of E given the F has occurred is denoted by this conditional probability, and it's rewrite in this way, right? There is no problem. And we can use the multiplication rule to write the intersection of n event probability in this way. Okay, in this way, the conditional one. Okay, conditional on one event E1, conditional on two events E1 and E2, and finally conditional on n minus one event intersections. That is called the conditional rule, and it's easy to understand for 2, right? For 2, we just rewrite the conditional probability, and be careful which event is given, okay? Which event is given. And this textbook, they would like to use event A, E, and F, or sometimes we would like to use this notation. Event B given in some other textbook, we would like to use this way, okay? It's the same. The event after the vertical line is the given event has occurred. Okay. Other notation. Okay, you might see in some other textbook. Part 2. A variable identity is, okay. How can we rewrite the probability of event E as those two? So here we use our notation. That will be probability of B, which is probability B giving A1 times probability A1 plus probability B giving A2. What is the relation for A1 and A2? A1 and A2, they are called the partition, okay? Partition, which means the union of those two gives the sample space, and the intersection of those two are null event. So A1 and A2 are partitions for the former partition. A1 and A2, what does A2 mean? Actually here A2 is the same. A2 is the same as A1's complement, right? So A1 and its complement form a partition for the sample space. That is the notation we would like to use. Form a partition for sample space S, right? And it's the same here, okay? You take the A1, you take event F as A1, you take its complement as A2, and we write the event E as event B. It doesn't matter, okay? It doesn't matter. So that is the special one, and we have this order of event. Okay, in the textbook they introduce this is order of event, and I think if you understand the probability of this one, okay, order of event, that will be much easier to work out. But we are going to skip this part. Okay, we are going to skip this part. That's why I mentioned here. The textbook mentioned the order of event. It's not much common in the probability part if you read the other textbook. Okay, skip this part. And the Bayes formula. Okay, the textbook gives the Bayes formula before the total probability theory. So if Fi is mutually exclusive event, they use Fi as the AI we used, okay? As the AI we used. If AI are disjoint event, then the probability Aj given event B, okay? We use the notation B. So what does this mean? That means the effect. Think about the cause-effect relation model, okay? So that means the effect B has been observed or the effect B has occurred, then what is the probability for the cause J comes, right? Because the event B, the effect B occurs, it might be several causes, right? If the causes is come from the J's one, what is the probability? So that will be the probability B given Aj times probability of Aj and over the probability of event B. How can we expand it, the probability of event B according to the total probability theory, right? This is called the Bayes formula, and my J can starting from 1, 2 until n, right? You can refer it as when the effect B occurs, what is the probability for the first cause comes from? What is the probability if it's because of the second cause? What is the conditional probability if it comes from the nth cause, right? It is come from the nth cause. I haven't seen the class is over. Let me finish here, okay? Let me finish here. You never mention I'm late, okay? I'm late 10 minutes. You don't care when I was late to start the class. Let me just finish the summary for the whole chapter, okay? So this denominator, this is in our textbook called the law of total probability. That is also we call the total probability theory in another textbook, okay? It's the same thing, okay? It's the same thing. Total probability theory, we use B, okay? We use B. So that is the summation. That is the summation I from n, and then it will be the conditional probability Aj, okay, J. This conditional probability means given the cause, okay, given the cause, the J's cause has occurred, then the conditional probability of the effect B occurs. Okay, that is different. So that is the total probability theory. In our textbook, they call the law of total probability. They are the same. They just would like to use the letter E and Fi. Okay, E and Fi. And finally, the independence. Okay, independence for two events is much easy, right? Independence of two events. If we call independence of three events, that should satisfy four identities altogether, right? All of the three event probability and any other two event out of the three. So So that is what we said. If we call E1, E2 until En are said to be independent, then any subset of those will be independent, which implies a lot of identity satisfied. Okay, that is the independence part. And finally, the conditional probability is also a probability which satisfies the axioms of number 3, and you can take this conditional probability as form the new sample space of F. Okay, form the new sample space as event F. You take event F as a new sample space. So that is I think all of those. Okay, all of those. We are not going to start chapter 4 this time. So we will stop here today.